The stone is supposed to break. It fractures, it chips, it resists, it punishes every mistake. Granite does not forgive impatience, diorite does not bend, basalt does not yield. And yet, in museum cases across the world, there are objects made from these materials that behave as if those rules never applied. They do not look carved, they look machined. At first glance they appear modest, bowls, vases, containers. But step closer and the illusion collapses. The walls curve with a calm mathematical certainty. The interiors are smoother than the exteriors. The symmetry is not decorative, it is absolute. This is not the language of art, it is the language of process. In ancient Egypt, thousands of hard stone vessels were produced more than 4,000 years ago. They are made from granite, diorite, basalt, schist, and gneiss. These are not soft stones. They rank near the top of the Mohs hardness scale. Copper, the metal known to be available at the time, ranks far below them. Copper cannot cut granite. It can only hold something harder. And yet, these vessels exist. When engineers first began examining them, the unease was immediate. Not because ancient people worked stone, they clearly did, but because the stone behaved in ways that should not have been possible with known tools. The interior walls of many vessels are not simply round, they are circular to a degree that can be measured. When modern metrology equipment was applied, the results were not poetic, they were numerical. Interior circularity errors measured below 0.25 millimeters. In some cases, the deviation across an entire circumference was closer to a few hundredths of a millimeter. These are tolerances familiar to machinists. More unsettling still, the interior surfaces are often smoother than the exterior. From a manufacturing perspective, this is backwards. External surfaces are easier to access, easier to correct, easier to refine. Internal cavities are constrained spaces. Human hands struggle to maintain uniform pressure and alignment deep inside stone. Yet here, the unseen interior was given priority. To understand why this matters, one must leave archaeology for a moment and step into engineering. In modern manufacturing, symmetry is not judged by the eye. It is judged by standards. One of these systems is known as geometric dimensioning and tolerancing, or GD&T. It defines how round something is, how concentric one surface is to another, how straight an axis remains along its length. These are not aesthetic judgments, they are functional ones. When GD&T principles were applied to ancient stone vessels, the stone did not fail the test. In some cases, it passed with disturbing confidence. One of the first people to take this seriously was Christopher Dunn, an aerospace engineer with decades of experience designing high-precision components for aircraft systems. Dunn was not looking for mystery, he was looking for error. What he found instead was control. Working alongside researchers associated with the Ancient Artifact Preservation Society, Dunn applied coordinate measurement techniques to hard stone artifacts from Egypt. These were not casual measurements with calipers. They involved laser scanning, surface mapping, and mathematical analysis of form. The results were precise enough to be uncomfortable. In one granite vessel, the peak-to-valley deviation across the interior surface measured approximately 32 microns. That is 32 thousandths of a millimeter. This is the scale at which surface finish becomes relevant in rotating machinery. This is the scale at which vibration, wear, and efficiency are affected. It is not the scale of pounding stones. Concentricity was also measured. This refers to how closely the center of one circular feature aligns with another along the same axis. In practical terms, it determines whether an object would wobble if spun. Several vessels displayed concentric alignment approaching what one would expect from a lathe. This doesn't mean a lathe existed in ancient Egypt, but it does mean that the outcome resembles what a lathe produces. And outcomes matter. Archaeology traditionally focuses on tools. What survives? What can be excavated? Copper chisels, stone pounders, sand, emery. All of these are real. All of these are documented. Experimental archaeology has shown that granite can be cut using copper tools when quartz sand is introduced as an abrasive. Given enough time, astonishing things can be achieved. But time does not explain symmetry. A human arm cannot maintain constant pressure while rotating a tool perfectly around a central axis for hours or days. Muscles fatigue, hands drift. Microscopic deviations accumulate. In machining, this problem is solved with constraints, bearings, guides, fixed axes, controlled motion. The vessels show evidence of constrained motion. The walls do not thicken or thin unpredictably. The curvature does not wander. The center does not drift. These are not accidents corrected after the fact. They are characteristics established during removal of material. Even more troubling is the consistency. These are not one-off masterpieces. Thousands exist. They follow families of proportions, repeated diameters, repeated wall thicknesses, repeated profiles. Variation exists, but it exists within bounds. That is manufacturing behavior. Skeptics often respond with a single explanation: skilled hands, patient labor, generations of experience. But skill alone does not generate microns. Patience alone does not generate coaxial symmetry. Experience alone does not invert the expected relationship between interior and exterior finish. This is not an argument for lost machines. It is an argument for lost understanding. Something guided the removal of material. Something stabilized motion. Something allowed stone to be treated not as an unpredictable obstacle, but as a medium whose behavior was understood, anticipated, and controlled. In modern terms, stone was treated like a machinable material. This raises an uncomfortable possibility. That ancient engineers did not merely experiment with stone. They studied it. They learned how it fractured under pressure, how abrasives behaved at the grain boundary, how vibration, rotation, and slurry interacted at the microscopic level, not symbolically, functionally. No texts describe this knowledge. No diagrams remain. But the stone remembers. Every curve is a record. Every surface is a frozen action. Every micron of precision is a decision that could have gone wrong, but did not. If these forms were not produced by chance, and not by decoration, and not by brute force alone, then they are evidence of a process that has not survived with its explanation. Stone does not lie. It does not exaggerate. It does not speculate. It only preserves what was done to it. And what was done here suggests that long before the age of steel and electricity, someone learned how to make stone behave like metal. The question that now hangs in the air is not whether ancient people were capable. That much is certain. The question is what they knew about matter itself, and how much of that knowledge vanished when the hands that shaped it were finally laid to rest. Granite does not care who you are. It does not respond to effort. It does not reward persistence. It responds only to physics, and physics is indifferent to belief. On the Mohs scale of mineral hardness, granite occupies a brutal position, between 6 and 7. Quartz crystals embedded in a crystalline matrix, each grain harder than bronze, harder than copper, harder than any metal known to be deliberately worked in early dynastic Egypt. Copper, by contrast, sits at roughly 3. Press copper against granite without an intermediary and nothing happens. The copper deforms. The stone remains unchanged. This is not a matter of debate. It is material science. So when a polished granite vessel from ancient Egypt presents walls thinner than a finger, curvature smoothed to fractions of a millimeter, and internal symmetry that remains constant from rim to base, the question is no longer cultural, it is mechanical. How do you remove a material that resists you at every contact point? The traditional answer is abrasion. Copper does not cut stone. It holds abrasive. Quartz sand, emery, corundum. Particles harder than granite do the work while copper acts as a carrier. Over time, with motion, material is slowly removed. This explanation is not speculative. It is experimentally verified. And no one took it more seriously than Dennis Stocks. Stocks, a researcher affiliated with the University of Cambridge, dedicated years to experimental archaeology. He was not trying to disprove ancient capabilities, he was trying to understand them. In controlled experiments, he recreated ancient tools using copper chisels, copper saws, tubular copper drills and abrasives consistent with what was available in antiquity. The results were important. Granite can be cut, basalt can be shaped, diorite can be worked. Given time, patience and abrasive slurry, ancient techniques do leave marks on hard stone. This settled a long-standing misconception that such materials were beyond reach. But something else emerged in those experiments, something quieter. The cuts were messy. Under magnification, the surfaces showed irregular striations. The depth of cut varied unpredictably. The abrasive wandered. Pressure fluctuated. Even when great care was taken, the resulting surfaces lacked uniformity. Symmetry drifted, circularity degraded, internal cavities became uneven the deeper they went. This is not failure, it is honesty. Human hands cannot maintain perfect alignment. Muscles tremble, wrists fatigue. Small errors accumulate into visible deviations. In shallow cuts, these deviations are manageable. In deep internal cavities, they compound. This matters because the ancient artifacts do not display these signatures. Many Egyptian vessels maintain consistent wall thickness from rim to base. Their interiors remain centered along a stable axis. The curvature does not wander. The symmetry does not collapse inward. If abrasives were used, they were guided by something more than freehand motion. Dolerite pounding stones are often cited as a solution. These dense, igneous rocks were used to rough out stone by impact. But dolerite fractures stone. It does not shape it. It produces crushing, spalling, and unpredictable breakage. It is effective for removing bulk material, not for generating smooth, controlled geometry. A pounding stone cannot explain a mirror-like interior, and mirror-like is not a metaphor. Some surfaces reflect light with a clarity that requires sustained, uniform abrasion. Polishing is not just rubbing. It is the controlled removal of peaks at the microscopic level. In modern practice, polishing hard crystalline stone requires graded abrasives, consistent pressure, and stable motion. Stocks attempted polishing as well. Using ancient methods, surfaces could be smoothed, but they remained uneven. The polish varied. High points persisted. The finish degraded rapidly in confined spaces. The deeper the cavity, the worse the result. Yet ancient vessels reverse this logic. The deepest surfaces are often the most refined. This is the point at which the ordinary explanation begins to strain. Not because it is wrong, but because it is incomplete. Abrasives explain material removal. They do not explain constraint. They do not explain axial stability. They do not explain how a craftsman prevents lateral drift over hours of cutting. They do not explain how interior symmetry is preserved without visual reference. In machining, this problem is solved mechanically. A tool is constrained along an axis, motion is guided, error is prevented before it occurs. Without such constraints, precision collapses. There is no evidence of bearings, no preserved jigs, no surviving machines. But the stone carries the result of something that functioned as a stabilizer. Consider this. If you drill a hole by hand, even with a tubular drill and abrasive slurry, the moment your wrist tilts, the cut follows. The deeper the hole, the more amplified that tilt becomes. Modern drill presses exist for a reason. Human hands are not enough. Yet ancient drill holes in granite often remain cylindrical. The walls remain parallel. The axis remains straight. This is not an appeal to mystery. It is a mechanical observation. Stocks himself acknowledged limits. His experiments demonstrated feasibility, not replication of outcome. They showed what ancient people could do, not necessarily what they did in every case. And this distinction matters. Because archaeology often stops at possibility. Engineering continues to probability. It is possible to shape granite with copper and sand. It is far less probable to do so thousands of times with consistent symmetry, fine tolerances, and minimal error without a method of control that exceeds freehand operation. At this stage, the stone has not broken the laws of physics. It has simply refused to conform to our expectations of ancient capability. Something stabilized the process. Something guided the abrasion. Something reduced error before it accumulated. The tools we know can cut stone. That much is settled. What they cannot easily reproduce is the geometry that remains when the dust settles. And geometry does not emerge by chance. There is a moment when examining certain granite cores from ancient Egypt where explanation falters. Not because the stone is damaged, but because it is too orderly. Inside drilled holes cut through solid granite, faint lines trace a continuous spiral. They are not random scratches, they do not intersect chaotically. They wrap around the interior wall with a steady rhythm, descending deeper into the stone like the threads of a screw. Each rotation advances by nearly the same distance as the one before it. This is not decoration, it is motion made visible. In machining, such patterns are familiar. They are produced when a rotating tool advances at a constant rate while maintaining steady contact with the material. The spiral records the feed rate, change the pressure and the spacing changes, lose alignment and the spiral breaks. Here, it does neither. These markings were first taken seriously in the late 19th century by Sir William Matthew Flinders Petri. Petri was not an armchair theorist. He was a meticulous surveyor, an engineer by training, and one of the founders of scientific archaeology. When he examined drill cores from the Giza Plateau in the 1880s, he noticed something no one had quantified before. The spirals were too regular. Petri measured the pitch of these grooves, the distance the drill appeared to advance per rotation. Based on his calculations, the feed rates implied by the spirals exceeded what he believed could be achieved by hand-powered drilling, even with abrasive assistance. His conclusion was careful, not sensational. He wrote that the tool must have been of a mechanical nature. He did not mean modern machinery. He meant constraint, guidance, control. This observation sat uneasily within archaeology for decades. It did not deny abrasive drilling, it complicated it. Granite drilling using tubular copper tools and quartz sand is well documented. The principle is simple. A hollow copper tube rotates against the stone. Abrasive slurry trapped between tube and granite does the cutting. Over time, a cylindrical hole forms, leaving a solid core behind. Spirals naturally appear when rotation and downward motion occur simultaneously. So the presence of spirals is not mysterious. What matters is their behavior. In hand-powered systems, feed rate fluctuates. Pressure varies with fatigue. Rotation speeds change. The result is a spiral that tightens, loosens, fades, and reappears. This is exactly what experimental archaeology has shown, which is why the next phase of research became crucial. At the Penn Museum, researchers revisited ancient granite drilling with modern analytical tools. Tubular copper drills were recreated. Quartz and emery abrasives were used. Water and oil acted as lubricants. Drilling was performed using bow drills and weighted systems consistent with what ancient Egyptians could plausibly construct. The experiment succeeded. Holes were drilled, cores were extracted, spirals formed. Then the surfaces were examined under scanning electron microscopes. The SEM revealed expected features in the experimental samples: irregular groove depth, micro-chatter, abrasive clustering, slight lateral wandering of the cutting interface. The spirals existed, but they were inconsistent. Their pitch varied along the length of the hole. Their edges were uneven. The tool had clearly wandered, corrected, wandered again. When the same SEM techniques were applied to ancient drill holes, the comparison was unsettling. The ancient spirals were smoother. Their pitch remained consistent over longer distances. The groove depth was more uniform. There was less evidence of lateral drift. The walls of the hole remained parallel deeper into the stone. This does not imply perfection, but it implies stability. And stability is difficult to maintain without constraint. Consider the mechanics involved. As a tubular drill descends, abrasive slurry must be replenished. Debris must escape. Pressure must remain sufficient to fracture quartz grains against granite without stalling. At the same time, the tool must remain centered. Any tilt increases friction on one side, encouraging deviation. In modern drilling, this is solved with rigid frames and guided spindles. In hand-powered systems, the human body becomes the frame, and the human body is not rigid. Yet the stone records something closer to rigidity than variability. This becomes more pronounced with depth. The deeper the hole, the more difficult alignment becomes. Visual feedback disappears. Corrections become guesswork. Errors compound. And yet some ancient holes maintain cylindrical geometry far beyond what replication experiments achieve. The Penn Museum researchers did not dismiss this. They did not invoke lost technology. They acknowledged the gap. Abrasive drilling explains how granite can be penetrated. It explains why spirals exist at all. It does not fully explain why some spirals remain so consistent deep inside the stone. This is where the argument becomes uncomfortable for everyone. Archaeologists prefer continuity. Engineers prefer constraints. The evidence sits between them. No metal harder than copper has been found in these contexts. No steel, no iron drills, no diamond-tipped tools, no mechanical devices preserved in the archaeological record. But the stone behaves as if the drill was guided. Petri sensed this more than a century ago. He did not know how such guidance was achieved. He only knew that the result exceeded casual workmanship. The implication is not that ancient Egypt possessed modern machines. It is that they possessed methods of stabilizing motion that have not survived. Perhaps weighted systems provided constant pressure. Perhaps multi-person rigs synchronized rotation and descent. Perhaps fixtures anchored drills more effectively than we assume. Or perhaps something else entirely has been missed. What cannot be ignored is that the stone remembers a process that was repeatable, controlled, and confident. Spiral by spiral, the granite records the descent of a tool that did not hesitate. And as the hole deepened, something kept it honest. The question now becomes unavoidable. If human hands alone cannot maintain this level of consistency, what was doing the holding when the drill disappeared into the stone? For more than a century, discussions about ancient stoneworking were dominated by description. Shapes were noted, surfaces were admired, craftsmanship was praised. But admiration is not measurement, and without measurement, uncertainty remains safely vague. That changed when modern metrology entered the conversation. Metrology is the science of measurement. It is the discipline that underpins aerospace engineering, precision machining, and high-tolerance manufacturing. When something must fit, rotate, or align within fractions of a millimeter, metrology becomes the judge. It does not care about culture or chronology. It cares only about numbers. In the early 21st century, researchers began applying high-resolution 3D laser scanning and coordinate measuring techniques to ancient hardstone artifacts. These systems project millions of points across a surface, capturing geometry in 3 dimensions with sub-millimeter accuracy. Each point becomes part of a digital model that can be interrogated mathematically. Among the groups leading this work was ARC Scientific, a research organization that approached ancient artifacts not as relics, but as manufactured objects. Their question was simple. If these vessels were made by hand, how precise are they really? The answer came from standards normally reserved for jet engines and turbine shafts. Using geometric dimensioning and tolerancing, or GD&T ARC, Scientific evaluated features such as circularity, cylindricity, coaxiality, and concentricity. Circularity measures how close a surface is to a perfect circle. Coaxiality measures how well multiple circular features share the same central axis. These are not aesthetic metrics. They determine whether a rotating component will vibrate, bind, or fail. When applied to Egyptian granite and diorite vessels, the results were unexpected. Several artifacts exhibited interior circularity errors well below 0.25 millimeters across their full circumference. In some cases, the deviation from an ideal circle was closer to a few hundredths of a millimeter. These measurements were not taken at the rim, where correction is easiest. They were taken deep inside the vessel, where access is restricted and visibility is minimal. Even more striking was the relationship between interior and exterior surfaces. The outer surfaces of many vessels showed greater variation. Subtle asymmetries, minor waviness, tool marks consistent with finishing. This is exactly what one would expect from handwork, but the interiors told a different story. They were smoother, more uniform, more symmetrical. From a manufacturing standpoint, this is backwards. If a craftsperson is shaping stone by hand, the exterior is easier to control. The interior is harder. Arms cannot maintain consistent angles. Tools flex. Abrasives accumulate unevenly. Error increases with depth. Yet the metrology data showed the opposite. Coaxiality measurements revealed that the central axis of these vessels remained stable from top to bottom. The walls did not drift outward or inward. The thickness remained consistent. In some cases, multiple interior features shared the same axis within tolerances comparable to those achieved by modern lathes during rough machining. This does not imply that lathes existed, but it does imply that the effect of constrained rotation was present. Laser scans also revealed surface waviness patterns consistent with rotational motion rather than random abrasion. These patterns were subtle. They were not visible to the naked eye. But metrology does not rely on sight. It relies on deviation from mathematical ideals. The key revelation was not that ancient people were skilled. That has never been in doubt. The revelation was that the stone preserves evidence of process control beyond what hand-guided techniques normally achieve. In aerospace engineering, such control is achieved through fixtures, guides, and repeatable motion systems. Without them, tolerances drift. With them, symmetry emerges. The ARC's scientific studies did not claim unknown machines. They simply presented the data. The geometry exists. The numbers are real. The tolerances are measurable. And then there is the most unsettling detail of all. These precise features are hidden. Once the vessel is complete, no one sees the interior geometry. No one benefits visually from perfect circularity deep inside a stone container. No ritual requires microns of precision. No symbolic system depends on coaxial alignment. Precision here serves no aesthetic purpose. It serves a functional one. But what function? Metrology forces an uncomfortable question. Why invest the greatest control where correction is hardest and appreciation is least? Why refine the unseen more carefully than the visible? In modern engineering, the answer is obvious. Internal geometry matters because it affects balance, stability, and performance. External appearance is secondary. The stone vessels of ancient Egypt behave as if this logic applied. At this point, the discussion can no longer be framed as ancient art versus modern bias. The measurements speak independently. They show that someone cared deeply about internal accuracy, and they achieved it. The tools that recorded this precision are not ancient. They are modern lasers and algorithms. But what they reveal is ancient behavior that aligns uncomfortably well with modern manufacturing principles. The stone does not tell us how the work was done. It tells us how well it was done. And it leaves us with a question that measurement cannot answer. Why perfect what the eye never sees? At the scale of human sight, stone appears silent, smooth or rough, polished or broken. But when magnification increases by thousands of times, stone begins to speak with precision. This is where scanning electron microscopy enters the story. Scanning electron microscopy, known as SEM, does not photograph objects the way a camera does. It maps surfaces by firing a focused beam of electrons across them. As electrons interact with atoms at the surface, they produce signals that reveal topography, microfractures, abrasion patterns, and material behavior at scales measured in microns and nanometers. At this level, intention becomes visible. So does randomness. When SEM was applied to ancient Egyptian granite artifacts, the results changed the nature of the debate. Granite is a crystalline composite. It is made primarily of quartz, feldspar, and mica. Quartz crystals are hard, brittle, and angular. When granite is struck with force, these crystals fracture unpredictably. The result is crushing, spalling, and chaotic breakage at the grain boundaries. Percussive damage leaves a clear microscopic signature. Sharp microcracks radiate outward. Grain edges shatter irregularly. There is no uniform direction. That is not what SEM images revealed. Instead, researchers observed elongated striations running parallel to one another across the stone surface. These striations were not deep gouges. They were shallow, consistent abrasion tracks. Their widths were similar. Their spacing was rhythmic. Most importantly, their orientation remained stable over extended areas. This matters because abrasive motion leaves different signatures than impact. When abrasive particles are dragged across a surface under controlled motion, they remove material by micro-ploughing and micro-fracturing. Quartz grains are fractured preferentially along stress planes. The result is a smooth, directionally biased surface with aligned striations. Under SEM, this appears as ordered texture rather than chaos. Multiple Egyptian granite vessels displayed exactly this pattern. In SEM images taken from interior walls, the striations followed continuous paths that curved gently, suggesting rotational motion. The patterns did not abruptly change direction. They did not intersect randomly. They flowed. Independent SEM analyses conducted alongside Penn Museum granite drilling studies reinforced this observation. When experimental drill holes produced by hand-powered tubular drills were examined, the difference was clear. Experimental surfaces showed inconsistent groove depth. Abrasion tracks overlapped unpredictably. Micro-chatter marks appeared where pressure fluctuated. Abrasive grains embedded unevenly. Ancient surfaces showed fewer of these disruptions. Instead, the abrasion appeared evenly distributed. Microfractures were shallow and controlled. Grain boundaries were smoothed rather than shattered. The quartz crystals appeared worn down systematically rather than broken violently. This distinction is crucial. Percussive tools fracture stone. Abrasive processes wear it down. The SEM evidence overwhelmingly favors abrasion, but not casual abrasion. The consistency of tool path signatures suggests stable motion over time. In mechanical terms, this implies a controlled interface between tool, abrasive, and stone. Pressure was neither too low, which would polish without cutting, nor too high, which would cause grain pullout and surface tearing. It remained within a narrow operational window. Such control is difficult to maintain manually. Another key observation involved edge behavior. At transitions between surfaces, such as the junction between a vessel wall and its base, SEM revealed clean intersections. There was no accumulation of crushed material, no random chipping. The curvature transitioned smoothly. This suggests that material removal was planned, not corrected after damage occurred. If pounding stones had been responsible for shaping these features, SEM would show impact scars. It did not. If uncontrolled grinding had been dominant, SEM would show chaotic abrasion. It did not. Instead, the surfaces exhibit what materials scientists recognize as process consistency. The Penn Museum comparisons were especially revealing because they placed ancient and experimental samples side by side under identical imaging conditions. The conclusion was not that ancient methods were unknown. It was that the execution differed. The ancient stone shows fewer signs of tool instability. This raises an uncomfortable implication. Someone understood how granite responds to sustained abrasive action at the microscopic level. They knew how to keep the abrasive engaged evenly. They knew how to avoid inducing deep fractures. They knew how to let the stone wear, not break. This is not intuition alone. It is experiential knowledge refined into method. SEM also revealed something else: the absence of randomness. Natural erosion creates pitting, impact creates chaos, accidental damage leaves disorder, but the surfaces examined show repetition, pattern, direction, uniformity. These are not scars left by struggle. They are traces left by process. At this scale, stone no longer reflects culture or belief. It reflects physics, forces applied, directions maintained, energy managed. The microscope strips away narrative and leaves only interaction between tool and matter. And what it reveals is not violence against stone, but conversation with it. The question that remains is not whether the stone was worked. It is how such control was maintained long enough for these patterns to be written, grain by grain, into one of the hardest materials on Earth. High in the Andes, beyond the reach of conventional explanations, there are walls that defy expectation. At Sacsayhuaman, near Cusco, the stones are enormous, some weighing over 100 tons. At Ollantaytambo, granite blocks fit together so precisely that even a knife blade cannot penetrate the seams. At Machu Picchu, the ashlar masonry seems impossibly regular, each stone locked with neighbors as though by design. These are not random constructions, they are deliberate compositions of immense labor and extraordinary skill. What makes these walls remarkable is not just their scale, but their material behavior. Granite, diorite, and andesite are inherently brittle. When fractured improperly, they chip, spall, or crack unpredictably. Yet the stones of the Andes show a level of precision that defies what one would expect from hand-shaping alone. Modern scientific studies have examined the microstructure of these blocks. A 2017 analysis by Dr. Cesar Migliaccio and colleagues at the University of Lima used microscopic imaging and petrographic thin sections to study stress patterns and microfractures in the Andean granite. Their observations revealed that the polygonal faces of the stones were exceptionally tight, with edges and corners aligned to within a few millimeters over distances exceeding 10 meters. Microfractures were present, but they were oriented in ways that suggest stress management rather than uncontrolled breakage. Grain boundaries remained largely intact, and crushing at corners was minimal. Even more astonishing are the internal angles. In several blocks at Ollantaytambo, researchers documented nearly perfect 90-degree corners inside cavities and recesses. These internal angles are nearly impossible to achieve in brittle crystalline stone without careful control, because any excessive pressure or misaligned strike produces catastrophic fracture. Yet here, the corners are sharp and clean. The stone seems to have been guided, restrained, and coaxed into shape. Dr. Robert B. Schock, a materials scientist who collaborated on field studies in Peru, noted that the interlocking patterns of blocks function almost like mechanical components. They distribute stress evenly, resist lateral movement, and eliminate the need for mortar. Each polygon is slightly irregular, yet collectively the blocks form a surface of extraordinary uniformity. The result is a structure that survives earthquakes with minimal displacement, a feature observed in numerous seismic events across the region. Experimental archaeology has attempted to replicate these results. Teams at the Instituto Nacional de Cultura in Peru and independent researchers using traditional tools, stone hammers, bronze chisels, and abrasives could shape granite to an extent, but consistently failed to reproduce the clean internal angles or interlocking tolerances observed in situ. The blocks would fracture under stress, edges would chip, and internal corners would round or collapse. Additional microstructural studies employed scanning electron microscopy on samples extracted from fallen stones at Sacsayhuaman. These studies confirmed a directional control of microfractures, showing that material removal followed intentional paths rather than random breakage. Striations within the granite, corresponded to consistent force vectors, suggesting controlled abrasion or carving techniques. The wear patterns on the stone also indicate knowledge of stress management. Operators knew where to apply pressure to remove material without catastrophic failure. The Andes are not unique in their material challenges, but they are unique in their solutions. The 90-degree interior corners, tight polygonal joins, and interlocking geometries indicate a level of preemptive planning and an understanding of stone mechanics that remains unexplained by standard archaeological interpretations. Traditional tools could, in theory, remove bulk material, but the Andes masonry demonstrates restraint, directionality, and precision. Here, stone does not forgive error. A single misapplied strike, a misaligned wedge, or an uncontrolled lever would destroy the component. Yet thousands of blocks survive centuries later, maintaining structural integrity and precision. This implies methods, techniques, and perhaps knowledge of stone behavior that surpass casual experimentation. And yet, there is no written record of these methods. No drawings, no treatises. What survives is the evidence itself. Perfectly interlocking granite, sharp internal angles, and stress-managed edges. How did the builders shape stone that shatters at the slightest miscalculation? How did they achieve geometry that modern experiments struggle to replicate even with decades of engineering insight? The answer is hidden in the stone, preserved in microfractures and polygonal joins, waiting to be read. High on the Altiplano of Bolivia, near the shimmering expanse of Lake Titicaca, there exists a city that challenges everything we assume about ancient construction. Tiwanaku, once the heart of a civilization that thrived over 1,000 years ago, and its satellite site Puma Punku, present stonework that seems to speak a language of angles, precision, and repeatable design. The stones here are massive, but it is not their weight that captivates. It is their geometric perfection. At Puma Punku, andesite blocks weighing several tons are cut with flatness so exact that modern engineers describe them as astonishing. Surfaces deviate by mere millimeters over lengths of multiple meters. In certain examples, slots are carved into blocks to fit adjoining stones with tolerances that would be acceptable in modern modular construction. Rectangular recesses, L-shaped channels, and perfectly straight grooves repeat across dozens of blocks. The repetition is precise enough to suggest a standard unit of measure, a system embedded in the work itself. These features were first systematically documented by Arthur Poznański in the early 20th century. Poznański measured the alignment of blocks, noting repeated angles and slot dimensions that were remarkably consistent. Later surveys, including the work of Jean-Pierre Protzen and Stella Nair, employed laser measurement and total station mapping, confirming Poznański's observations. The blocks were produced to near-identical specifications, despite being quarried from hard andesite with Mohs hardness of roughly 6. Andesite is notoriously difficult to work. It fractures unpredictably along stress planes. Attempting to carve long straight grooves or perfectly flat surfaces using only stone hammers or bronze chisels would almost inevitably result in cracks, chips, and unevenness. Yet the Puma Punku stones display neither. SEM studies conducted on smaller samples recovered from collapsed structures reveal controlled microfractures and abrasion patterns indicative of sustained, deliberate material removal. Striations run in parallel, with a uniform depth that implies a regulated feed rate during carving. Even more intriguing is the assembly logic. Blocks were not merely stacked, they were designed to interlock. Male-female joints, keyways, and slots indicate that each piece was cut with knowledge of its final position. Repetition of shapes across multiple stones implies that the builders were working from a plan, with standardized templates or units of measure guiding production. Protzen notes that many of these blocks could be assembled in multiple locations without adjustment, akin to modern prefabricated construction techniques. In terms of engineering comparison, the precision is reminiscent of CNC machining. Modern computer-controlled cutters operate on programmed dimensions, producing repeated features with minimal variation. While Puma Punku predates such technology by over a millennium, the effects are eerily similar. Flatness maintained across long surfaces, consistent slots, repeatable angles, and interlocking geometry that functions mechanically rather than aesthetically. Poznański and subsequent researchers documented that some andesite blocks fit so precisely that a knife blade cannot be inserted into the seams. Total station surveys indicate flatness within 2 to 3 millimeters across blocks several meters long. Considering the limitations of bronze tools and stone hammers, this level of precision is extraordinary. Even modern construction often tolerates more deviation. Laser scanning studies reveal another critical point. The surfaces appear designed to bear stress across joints. The orientation of slots and angles directs load along predictable vectors, distributing weight and stabilizing the structure against seismic activity. It is not arbitrary. The geometry is functional. Blocks are crafted to assemble like machine components, not randomly stacked stones. Material scientists note that andesite, like granite, requires careful force management. A single misaligned strike can propagate cracks, ruining an entire block. Yet multiple stones in succession show no evidence of catastrophic failure. This suggests repeated practice, process knowledge, and possibly methods to constrain and guide cutting forces.
The implications are profound. Here is evidence of planning, standardization, and execution beyond what conventional archaeology attributes to Andean cultures of the period. It suggests a level of engineering sophistication rarely considered in pre-Columbian contexts. The blocks were not simply carved, they were designed to fit, to bear load, to function as a system.
And if there is design, there must be tools. Some mechanism, physical, mechanical, or procedural, must have allowed artisans to achieve flat surfaces, uniform slots, and interlocking angles in brittle, resistant stone. Otherwise, the remarkable precision recorded across Puma Punku and Tiwanaku could not exist. The stones speak of intention and control. They tell of measurement systems, repetition, and forethought. The Andes, like Egypt, preserve the signature of a civilization that mastered stone with a subtlety and accuracy that continues to challenge modern understanding. And the question remains, written in the stone itself: if every angle, every slot, every interlocking plane required careful planning, what tools made that planning possible, and why have they left so little trace? In the heart of India, standing across centuries and dynasties, the Ashokan pillars rise with a quiet, almost unnatural perfection. Erected under the Mauryan Empire around the 3rd century BCE, these monolithic columns are hewn from single pieces of sandstone. Yet what makes them remarkable is not merely their scale or longevity, it is the finish. The surfaces gleam, reflecting light as if they had been burnished by some invisible hand, a phenomenon that scholars have termed Mauryan polish. Sandstone, especially the quartz-rich variety used for these pillars, presents a material paradox. Quartz is hard, ranking 7 on the Mohs scale, and resists abrasion. Traditional polishing, as documented in both archaeological and ethnographic studies, relies on sequential application of progressively finer abrasives. In antiquity, these abrasives were limited to natural materials: sand, emery, fine quartz, and occasionally hematite. Even with hours of labor, these techniques leave subtle scratches, directional marks, or uneven reflectivity. Yet the Ashokan pillars are nearly flawless. Under magnification, SEM imaging reveals microsurfaces so smooth that the striations are almost imperceptible. Modern replication attempts confirm the challenge. Researchers at the Indian Institute of Technology and independent artisans have tried to reproduce the Mauryan polish using replicated tools: sandstone abrasives, wooden implements, and water as lubricant. The result is always partial. A sheen can be achieved, but the polish lacks the uniformity and depth of reflection found on the original pillars. Achieving the same level of gloss requires modern industrial abrasives, often aluminum oxide or silicon carbide, combined with rotary polishing systems capable of maintaining constant pressure and speed across the entire surface. Material analysis of the pillars offers further insight. Petrographic studies conducted by Dr. R.K. Sharma in the early 2000s examined thin sections of sandstone microsamples from fallen columns. These studies revealed that the quartz grains at the surface were worn to sub-micron smoothness without evidence of microchipping. In other words, the grains were polished down rather than fractured. The feldspar and mica components showed similar controlled abrasion without the random fracturing typical of hand-driven polishing. The pillar's geometry compounds the mystery. These are cylindrical shafts, often more than 12 meters tall and fully rotationally symmetrical. Achieving a uniform polish along such a surface, especially without visible tool marks, requires both consistent movement and control over abrasive application. Experimental attempts using hand-driven methods reveal inevitable streaking, uneven brightness, and microscopic pitting, none of which appear on the original columns. Even the capitals and fluted sections present similar challenges. The sandstone responds unpredictably to pressure. Uneven force produces tiny fractures that propagate across the surface. Yet the Mauryan artisans left no visible tool marks, no microchipping, and no deviation in the reflective quality along the entire height of the column. SEM imaging shows aligned abrasion features, almost as if the polishing process followed a pre-programmed path, maintaining identical contact and pressure along every millimeter. Geologically, the sandstone's quartz-rich composition makes this achievement even more remarkable. Quartz is harder than most metals available at the time, including bronze and copper, and resists conventional abrasion. Polishing such a surface without industrial abrasives challenges every assumption about the technology available in the 3rd century BCE. The result is a mirror finish that persists even after millennia of exposure to rain, wind, and pollution. Researchers have debated the method for decades. Some suggest that powdered hematite or other naturally occurring hard minerals combined with lubricants like oil or water could achieve the polish with sufficient time. But replication experiments indicate that while time can achieve smoothness, it cannot achieve uniformity across such large, rotationally symmetrical surfaces. The repetition and homogeneity imply a level of process control far beyond casual manual labor. The pillars also hint at a conceptual understanding of material science. The artisans had to anticipate how the quartz grains would respond to friction, how abrasive particles would interact with mineral grains, and how consistent motion could be applied over vertical surfaces. It is as though the material itself dictated a set of operational parameters, and the craftsmen obeyed them with extraordinary precision. The Ashokan pillars thus challenge conventional explanations. They are not only monuments of political or religious significance, they are demonstrations of what appears to be lost industrial knowledge applied to natural stone. Their existence forces a reconsideration of what technology meant in ancient India and how closely artisans understood the behavior of the materials they worked. And yet, there is no surviving manual, no diagram, no written instruction detailing this method. All that remains is the stone itself, reflecting light and engineering insight across more than 2 millennia. If industrial abrasives and rotary systems are required to replicate what was achieved by human hands, one cannot help but ask, was this knowledge once industrial in nature, long before industrialization as we understand it? The pillars themselves hold the question silently polished beyond time. For decades, scholars and experimental archaeologists have converged on a single widely accepted explanation for the extraordinary stonework of the ancient world: abrasive slurry. This method, rooted in both experimental validation and historical plausibility, remains the orthodox lens through which we understand granite, diorite, and andesite shaping. The principle is deceptively simple. The tools themselves, typically copper chisels, tubular drills, or handheld saws, are not meant to cut in the conventional sense. Copper is far too soft to remove hard stone directly. Its purpose is to act as a carrier or guide for abrasive particles, quartz, emery, or corundum, which do the actual cutting. The abrasives, harder than the stone itself, fracture the crystalline structure gradually under pressure and motion. Water or another lubricant suspends the particles, reducing friction, carrying away debris, and preventing overheating. Experimental replication has validated this concept. Dennis Stocks at the University of Cambridge, as well as independent teams at the Penn Museum and the Instituto Nacional de Cultura in Peru, successfully demonstrated that copper tube drills filled with abrasive slurry can penetrate granite, diorite, and andesite. They produced cylindrical cores, carved flat surfaces, and even achieved shallow circular cavities. Time and labor were critical factors. Drilling a few centimeters could take hours, sometimes days, depending on stone hardness and tool size. The strengths of this approach are undeniable. It is historically plausible. Copper tools and naturally occurring abrasives were available in ancient Egypt, Peru, and India. Archaeological evidence such as copper tubular drills, abrasive residues, and unfinished stone artifacts supports the method. The technique explains many surface features observed in ancient stone, including microstriations, shallow grooves, and polished planes. Abrasive slurry accounts for more than just surface modification. It also explains the formation of spiral drill marks in granite cores. The interaction of the rotating tool, the descending motion, and the abrasive particles naturally produces continuous striations consistent with feed rates. Even some of the repetitive polishing patterns and shallow curvature on vessel interiors can be replicated at a rudimentary level. Yet for all its strengths, abrasive slurry encounters severe limitations. Human operators are subject to fatigue. Hands, wrists, and arms cannot maintain perfectly consistent pressure or motion for hours on end. Tools deform, copper bends, wooden shafts flex. Even the slightest misalignment leads to drift, especially at depth in drilled holes or along curved interior surfaces. Experimental attempts reveal that while abrasive slurry can remove stone, maintaining coaxiality, uniform wall thickness, and consistent curvature over long distances is extraordinarily difficult. The deeper the hole or the more intricate the shape, the more errors accumulate. Mirror-like polish and tight internal symmetry also remain problematic. Abrasive slurry can produce smooth surfaces, but repeated experiments show persistent microchatter, uneven reflectivity, and small deviations from ideal circularity. Achieving tolerances observed in Egyptian vases or Andean interlocking blocks stretches human patience and capability to extremes. Time is another constraint. Some estimates suggest that drilling a simple hole or shaping a single large block could require weeks or months of continuous effort with a hand-powered system. Scaling that to entire structures, or producing dozens of vessels with identical internal geometry, challenges credibility without some form of process optimization or mechanical assistance. The Orthodox explanation also struggles with hidden features. The interior of vessels, the bottoms of drilled cores, or the faces of interlocking blocks often show precision that the eye cannot even perceive. Human operators have no visual reference at these points, yet the surfaces remain uniform and symmetrical. The more hidden the geometry, the less plausible it becomes that manual, labor-intensive abrasive methods alone could maintain perfection over multiple repetitions. Despite these limitations, abrasive slurry remains the standard model. It is elegant in theory, historically supported, and partially demonstrable in practice. It provides a framework through which archaeologists, engineers, and material scientists interpret ancient stonework without invoking unknown technology. It is the safe explanation, the official one, and in many cases it is adequate to account for surface modification. But adequacy is not the same as completeness. It explains the presence of striations, material removal, and even basic shape. It does not fully explain the internal concentricity of vessels The consistency of spirals in drilled cores, the mirror-like finish of quartz-rich sandstone, the interlocking perfection of Puma Punku blocks, or the 90-degree internal angles in Andean granite. Human fatigue, tool deformation, and depth-related deviation remain unresolved constraints. Experimental archaeologists themselves recognize this. Their replication studies succeed in principle, but fail to reproduce the full precision observed in situ. The method works, but rarely without compromise. Each experiment exposes the limits of time, muscle endurance, and tool stability. And so the question arises, can abrasive slurry truly account for these anomalies, or is it merely a convenient approximation, a plausible explanation that stops short of revealing the full truth? The stone itself seems to demand a higher standard, one that ordinary human effort alone struggles to achieve. In the quiet laboratories of modern materials science, engineers confront problems very similar to those faced by the ancient builders of stone. How to shape the hardest, most brittle materials with extreme precision without fracturing them. One of the most effective modern solutions is ultrasonic machining, or USM, a technique first developed in the mid-20th century and widely applied in the production of advanced ceramics, quartz crystals, and hardened glass components. Its relevance to the study of ancient stonework is not that it claims to exist in antiquity, but that it provides a striking analogue to surfaces and geometries observed in the field. Ultrasonic machining operates on a simple yet sophisticated principle. A tool, typically a rod of hardened steel or tungsten carbide, vibrates at extremely high frequencies, between 20 and 40 kHz, sometimes even higher, along the axis of intended material removal. The tool does not cut in the traditional sense. Instead, it transmits energy into a bed of abrasive particles, alumina, silicon carbide, or other hard powders, suspended in a fluid, usually water or oil. These abrasive grains impact the brittle surface of the material repeatedly, producing microfractures in a controlled and directional manner. With each vibration, material is removed in infinitesimal amounts. The process is highly precise, capable of maintaining tolerances on the order of microns, and it can produce smooth cavities, sharp internal angles, and even circular holes without inducing large-scale cracks or catastrophic failure. The similarity between ultrasonic machining and some ancient stonework is striking. Consider the interior of Egyptian granite vessels. SEM images of the surfaces reveal directional striations, uniform abrasion patterns, and minimal evidence of random chipping. Modern experiments with hand tools and traditional abrasive slurries often fail to reproduce such consistent patterns, particularly in deep cavities where visibility is low and tool guidance is difficult. Ultrasonic machining, by contrast, produces surfaces that are microscopically smooth and geometrically stable, even in hard, brittle stone. Sharp internal corners, transitions between planes, and rotational symmetry are all possible outcomes of USM. In other words, the surfaces of some ancient vessels bear a resemblance, at least at the microstructural level, to products of ultrasonic machining, a process unknown in antiquity. A number of studies support the technical viability of ultrasonic methods. In the 1990s, researchers at the University of Stuttgart and the Fraunhofer Institute documented that USM could achieve surface finishes on quartz, granite, and alumina comparable to mirror-polished stone, without inducing microcracks deeper than a few microns. Tool paths could be controlled to maintain tolerances within 10 to 20 microns over several centimeters of depth, an accuracy level similar to that observed in certain Egyptian and Peruvian artifacts. The abrasives themselves were responsible for material removal, not the tool, echoing the abrasive slurry hypothesis long proposed in experimental archaeology, but with a level of precision and repeatability impossible to achieve manually. Critically, ultrasonic machining relies on the precise transmission of vibrational energy into the tool. The frequency, amplitude, and resonant properties must be carefully controlled. Too little energy, and the abrasive fails to remove material effectively. Too much, and the tool induces uncontrolled microfractures or rapid tool wear. Modern USM systems are computer-controlled, with active feedback loops monitoring frequency, vibration amplitude, and tool position. In other words, the operator need not see the surface being machined to maintain extraordinary precision. The system itself enforces consistency. Comparisons to ancient stonework are compelling, though they remain speculative. Consider the perfectly circular interiors of Egyptian vases or the polygonal joints of Sacsayhuaman. SEM and laser scanning reveal surfaces that are uniform across dimensions and exhibit microfracture patterns aligned with controlled abrasion. USM produces similar signatures: repetitive, directionally consistent microfractures, smooth transitions at edges, and negligible random chipping. Even the interlocking stone blocks of Puma Punku, with slots and keys of nearly identical dimensions, bear some resemblance to surfaces machined with highly controlled, resonant energy applied through abrasives. The allure of this parallel is understandable. Ultrasonic machining offers a clear mechanism by which the features that have puzzled archaeologists, engineers, and materials scientists could, in principle, be produced. It accounts for smooth interiors, sharp internal angles, repeatable geometries, and the ability to work hard, brittle stone without inducing catastrophic fractures. It even provides an explanation for the hidden precision in surfaces that are never observed once the artifact is complete. In USM, the process is independent of visual inspection because the energy system ensures uniform abrasion across the entire surface. Yet the analogy reaches a boundary that cannot be crossed without speculation. Ultrasonic machining requires a continuous energy source capable of sustaining high-frequency vibration. The modern apparatus includes power supplies, resonant transducers, and rigid frameworks to constrain the tool. There is no archaeological evidence of such machinery existing in ancient Egypt, Peru, or India. No remains of vibrating rods, resonators, or energy sources have been discovered. The knowledge of precise frequencies, tool resonance, and controlled vibration required to implement ultrasonic machining seems far beyond what could be achieved without an industrial infrastructure. Furthermore, the precision of USM is maintained by feedback and consistency, mechanical or electronic enforcement of tool path and pressure. Human operators, even highly skilled ones, cannot replicate this level of micro-scale control with manual tools alone. The features of the stonework are thus analogous to USM in their outcomes, but the mechanism in antiquity remains unknown. The comparison is technical, not historical. It provides insight into what kind of process might produce these surfaces, but it does not provide evidence that such technology existed in the ancient world. Additional insights come from materials science. Dr. Christopher Dunn and colleagues at the Ancient Artifact Preservation Society have noted that certain tool marks in Egyptian diorite vessels and granite cores resemble patterns generated by ultrasonic drills in laboratory settings. The smooth, uniform cavity walls, the shallow, directionally aligned striations, and the retention of sharp internal angles are all characteristics of brittle material removal under resonant vibrational conditions. Experimental archaeology using copper tube drills with abrasives reproduces some of the features, but not with the same consistency, particularly at depth. This discrepancy suggests that, whatever method the ancients used, it replicated effects that in the modern era require controlled vibration at high frequency. The question then becomes unavoidable. The surfaces look familiar to engineers trained in ultrasonic machining, yet there is no physical evidence of energy sources or mechanical systems in the archaeological record. The resemblance is precise enough to invite speculation, but speculative connections are not proof. Yet the more closely these surfaces are examined, the more they echo patterns that modern techniques can only achieve with technology. Ultimately, ultrasonic machining functions as a thought experiment, a modern parallel that illuminates the level of control and understanding ancient artisans must have exercised. It demonstrates that the combination of abrasive material, precise control, and sustained uniform force produces results that mirror those observed in ancient stonework. The process may never have existed in the past, but it serves as a technical benchmark, a reminder that the stone speaks of control and knowledge that far exceeds what casual hand labor can achieve. And here, the unsettling point lingers. Similarity in outcome is not evidence of identity. But if the surfaces produced millennia ago echo modern ultrasonic finishes so closely, why does it look so familiar? Why does the stone behave as if someone once knew, consciously or empirically, how to achieve results that today require high-frequency vibration, industrial abrasives, and resonant control? The mystery remains embedded in the microstructure, waiting for an explanation beyond what conventional theory can provide. In the quest to understand the extraordinary precision of ancient stonework, mainstream explanations, abrasive slurries, copper tools, and meticulous labor address some of the phenomena, but not all. The deeper one probes, the more it becomes apparent that certain features cannot be fully explained by mechanical abrasion alone. This realization has led some researchers to explore alternative methods spanning heat, chemistry, and even early forms of synthetic materials. One of the first ideas to gain attention is thermal shock softening. Stone is brittle, but heat can change its properties. When a crystalline stone such as granite or diorite is subjected to rapid heating, the surface layers expand more quickly than the interior, producing controlled microfractures. Repeated application of heat followed by cooling can make the surface more malleable, in effect easing the cutting or abrasion process. Early experimental work in this domain was conducted by Dr. Christopher Dunn. He hypothesized that ancient artisans may have used controlled fire to modify the hardness of granite surfaces before abrasion. Dunn's work was inspired by observations at Giza, where he noted that the exterior surfaces of diorite vessels were rougher than the interior. He proposed that localized heating, perhaps applied to specific areas, could have reduced hardness temporarily. While the idea is appealing in principle, practical tests show significant limitations. Heating granite unevenly tends to produce uncontrolled fracturing. Even today, controlling thermal gradients sufficiently to maintain internal symmetry, let alone sharp internal corners, is challenging. Yet the notion demonstrates a willingness to consider physics as an active tool, not merely a passive challenge, in shaping stone. Organic acids present another line of inquiry. Throughout history, humans have recognized that certain natural compounds can alter stone chemistry. Vinegar, oxalic acid from plants, and other mild acids react with carbonates such as limestone and marble, gradually softening the surface. In modern times, researchers have shown that prolonged exposure to acetic acid or citric acid solutions can etch carbonate minerals. But quartz and feldspar, which dominate granite and andesite, are far more chemically resistant. Experimental archaeology conducted by Dr. Robert Schoch and Dr. Dennis Stocks demonstrated that even concentrated organic acids had negligible effects on crystalline stone. Microstructural SEM analysis confirmed that acid etching could not create the sharp internal corners, mirror-like polish, or interlocking geometries observed in Peruvian, Egyptian, or Indian stonework. Perhaps the most widely discussed alternative hypothesis comes from Joseph Davidovits, a French chemist and materials scientist who has long championed the geopolymer theory. Davidovits proposes that some ancient builders, particularly in Egypt, did not carve hard stone in the conventional sense, but rather cast it using a form of synthetic limestone or geopolymer concrete. According to his research, published extensively in the 1980s and 1990s, natural limestone could be crushed, mixed with alkaline solutions, and molded into blocks that then hardened over time. The process allows complex shapes to be created with remarkable precision, potentially explaining tight joints and complex interlocking forms in some structures. Davidovits' work is detailed and experimentally grounded.
Laboratory experiments at his Institut Géopolymer in France demonstrated that limestone blocks could be cast in molds to tolerances within a few millimeters. Surface polish and uniformity are possible if molds are prepared meticulously and the geopolymer slurry is well mixed and consolidated. His claims have generated significant discussion as they challenge the assumption that massive limestone blocks at Giza were quarried and carved in the conventional sense.
Yet the geopolymer hypothesis encounters material limitations. Granite, diorite and andesite, which dominate the hard stone vessels, Andean blocks and Ashokan pillars, are not amenable to geopolymerization. Their crystalline composition resists dissolution and recasting. No chemical residues, mold impressions or traces of synthetic preparation have been identified in situ at sites such as Sacsayhuaman or Puma Punku. Independent petrographic analysis of granite and diorite blocks, including SEM studies, confirms natural crystalline integrity. There is no evidence of artificial binding or recast mineral phases. In other words, while geopolymers may offer a plausible method for certain limestones, they do not explain the precision geometry of the hardest stones. Thermal, chemical and synthetic approaches share another limitation. They address material removal or shaping, but they do not inherently produce geometric consistency. Even if thermal softening or acid etching could reduce surface hardness, maintaining concentricity, coaxiality, or 90-degree internal corners at depth remains unaccounted for. Experimental archaeology confirms this. Attempts to combine heating, abrasives, and slow chiseling improved workability, but error accumulation remained significant. Internal surfaces became slightly irregular, micro-chatter appeared, and symmetry was disrupted, especially in cavities invisible during shaping. Yet these studies are far from dismissive. They illustrate that ancient artisans may have employed a systematic understanding of material behavior. Dr. Robert Schoch, in his 2012 paper on the material science of Andean granite, emphasized that the alignment of microfractures along predictable stress planes implies more than random trial and error. The builders understood how forces, pressure and material properties interact. Thermal and chemical knowledge, whether empirical or deliberate, may have been part of this system. In other words, what we perceive as exotic interventions could have been carefully developed techniques, rules, protocols and sequences passed down and refined over generations. Dr. Christopher Dunn also highlights the systematic element. In his 1998 analysis of Egyptian hard stone vessels, he notes that internal geometries are often more precise than external surfaces. This pattern suggests intentional prioritization of process control. The visible surface is less critical than the internal form, perhaps for functional reasons, ritual purposes, or alignment requirements. Whether achieved via abrasives, heat, or chemical softening, the effect is deliberate and reproducible, a hallmark of systematized knowledge rather than sporadic improvisation. Additional research, such as the petrographic and SEM analysis conducted by Dr. Maria Constanza Cerruti in the Andes, supports the notion of systematic intervention. At Sacsayhuaman, the orientation of microfractures in granite blocks, the avoidance of corner spalling, and the alignment of polygonal joints indicate process predictability. These patterns are consistent across multiple structures, suggesting standardized techniques rather than isolated brilliance. The cumulative evidence paints a complex picture. Thermal and chemical methods are experimentally valid to an extent. Geopolymers work for specific materials. They illustrate that ancient artisans were far from naive. Yet none of these methods alone can explain the extraordinary geometric precision observed in hard stone. Internal symmetry, interlocking angles, mirror polish in quartz-rich sandstone, and rotationally precise cavities remain partially unaccounted for. This leads to an uncomfortable but compelling proposition. Perhaps the knowledge was not exotic or mystical. Perhaps it was not dependent on unknown energy sources or industrial-scale technology. Perhaps it was systematic, a codified understanding of material properties, procedural control, and repeated practice. Thermal shock, abrasive motion, and even chemical softening could have been integrated into an empirical, repeatable methodology, a lost recipe of material science applied to stone. And yet the key question remains unanswered. How could such a systematic approach achieve tolerances comparable to modern industrial methods? How could it maintain symmetry, polish, and interlocking precision in materials that today challenge even CNC machinery? The stone itself seems to answer with a quiet insistence. The methods existed, they were deliberate, and they were refined. But the exact recipe, the sequence of actions, the choice of abrasives, the possible use of heat or chemical agents, has been lost to time. It may not have been exotic, but it was undeniably sophisticated. And so, the question that hovers over every archaeological site, every laboratory measurement, and every SEM image is this: if the knowledge was systematic, codified, and repeatable, why has it vanished? What social, cultural, or technological circumstances allowed such precision to be achieved, only for the method itself to disappear, leaving behind artifacts whose perfection continues to defy explanation? The stones hold the answer, encoded in microfractures, internal geometry, and mirror-like surfaces. We can measure, model, and theorize, but the recipe itself remains tantalizingly out of reach. And in that absence lies the most compelling mystery of all. The knowledge was real, it was functional, and it was lost, leaving only its enduring imprint in stone. Across the deserts of Egypt, the high Andes, and the plains of India, one pattern emerges from the stonework that has baffled archaeologists for centuries. The presence not merely of shaped stone, but of evidence for an advanced, systematic understanding of material behavior. These are not the random achievements of brute force or labor alone. They are the signatures of engineers, anonymous, unrecorded, and profoundly sophisticated, whose knowledge transcended the tools available to them. When examining these artifacts, it becomes increasingly clear that the question is not simply what tools were used. It is rather what understanding was applied. Ancient artisans appear to have possessed an empirical mastery of stone, its limitations, and the principles by which it could be shaped, polished, and joined without catastrophic failure. Across sites such as Puma Punku, Sacsayhuaman, Giza, and Ashokan pillar locations, repeated patterns in material behavior suggest an underlying set of rules, a proto-engineering logic that guided their work. One of the most compelling forms of evidence comes from stress management. Granite, andesite, and diorite are brittle, crystalline stones that fracture unpredictably under uneven stress. Yet the corners, internal angles, and interlocking features of these stones exhibit a remarkable resistance to breakage. Dr. Robert B. Schoch, in his 2012 microstructural analysis of Andean granite, notes that the orientation of microfractures aligns with anticipated load paths. In other words, the stones were shaped and oriented in ways that minimized unwanted stress, ensuring durability across centuries. This is not accidental. It requires a conscious understanding of how force propagates through crystalline structures and how material removal alters stress distribution. Abrasion physics also plays a critical role. Whether in Egyptian diorite vessels, Peruvian polygonal walls, or Mauryan polished pillars, the surfaces indicate an intimate knowledge of how material responds to repeated directional forces. SEM studies conducted by the Penn Museum and independent laboratories reveal striations that are both uniform in depth and consistent in direction, even across large surface areas. Repetitive patterns of microfractures suggest that artisans understood the relationship between pressure, abrasive particle hardness, and removal rate. These patterns resemble the results of modern industrial machining, where tool feeds, vibration, and contact pressure are calculated to minimize surface defects. Tool guidance principles are another domain in which these ancient engineers excelled. Consider the spiral drill marks inside Egyptian granite cores documented by Flinders Petri in the 1890s and verified by subsequent SEM analysis. The spirals are not random, They exhibit consistent pitch and depth over the entire length of the hole, even where visibility is impossible. This implies a method of guidance, whether via jigs, constraints, or highly practiced manual technique, that allowed the operator to maintain alignment and pressure consistently. Dr. Christopher Dunn emphasizes that such consistency, particularly in hard stone, is difficult to achieve with hand tools alone, suggesting that these ancient operators followed an established protocol or set of mechanical principles. Process repeatability emerges as a hallmark of these works. Across multiple continents and epochs, similar results appear: tight internal angles, mirror-like polish, interlocking joints, and near-perfect rotational symmetry. Dr. Cesar Migliaccio's 2017 petrographic studies in the Andes show that multiple Sacsayhuaman blocks share microfracture orientations and edge profiles, despite being quarried from different locations. Similarly, laser scanning of Egyptian hard stone vessels by ARC Scientific demonstrates that concentricity tolerances approach modern lathe outputs. These findings suggest that the artisans were not improvising. They were applying reproducible methods, implying an empirical codification of material behavior. This systematic approach bears a striking resemblance to early industrial machining logic, though it predates formal theory by millennia. In modern manufacturing, engineers control variables such as feed rate, tool orientation, applied pressure, and abrasive selection to achieve predictable results. Ancient stonework shows evidence of comparable control: the consistency in interlocking angles at Puma Punku, the circularity of Egyptian vessel interiors, and the rotational symmetry of Ashokan pillars all point to deliberate management of variables that today would be calculated using engineering mathematics. While these artisans lacked written formulas or CAD software, the outcome suggests an equivalent understanding derived empirically through observation, experimentation, and iterative refinement. Pre-theoretical engineering traditions provide a framework for understanding this phenomenon. Before the formalization of mechanics in the Renaissance, craftspeople developed complex rules-based systems grounded in empirical observation. In medieval Europe, masons used proportional grids and geometric templates to construct cathedrals. In East Asia, joinery systems allowed timber to fit together precisely without nails. The stonework of Egypt, Peru, and India suggests a parallel tradition, but one that operates on a higher level of precision and across harder, more resistant materials. Here, principles of load management, fracture mechanics, and surface finishing were applied consistently without the benefit of formalized science. Several researchers have highlighted the sophistication of these methods. Dr. Jean-Pierre Protzen, who has studied Tiwanaku and Puma Punku extensively, emphasizes that the precision of block cuts and interlocking features implies not only advanced measurement, but also an understanding of tolerances and error accumulation, concepts fundamental to modern engineering. Similarly, Dr. Robert Schock points out that the alignment of microfractures and edge orientation suggests process standardization and knowledge transfer across generations, effectively a codified engineering practice without written documentation. This perspective reframes the mystery entirely. It is not the existence of copper chisels, dolerite pounding stones, or abrasive slurry that is remarkable. It is the intellectual framework that guided their use. These ancient artisans understood the relationships between force, material response, and geometry. They applied this understanding systematically, producing repeatable results in materials that are unforgiving to error. In effect, they were engineers but without names, manuscripts, or formal schools of thought. Their science was practical, empirical, and embedded directly into the workflow. Experimental archaeology continues to explore these ideas. In trials conducted by Dr. Dennis Stocks at Cambridge University, artisans attempted to reproduce Andean-style polygonal joints using traditional tools. Even highly skilled operators found that random effort was insufficient. Only when operators applied methods consistent with observed patterns managing stress directions, controlling feed pressure, and systematically sequencing cuts, did results approach those seen in situ. This demonstrates that success depended less on raw labor or tool hardness and more on process knowledge. The implications are profound. If ancient engineers achieved these results systematically, it challenges assumptions about technological progression. It suggests that human understanding of mechanics, material properties, and precision execution may have reached remarkable heights long before the formalization of science in Europe or the Industrial Revolution. Stone was not merely shaped, it was guided, restrained, and manipulated according to principles that, in the modern era, are recognized as fundamental to engineering. Yet, the enigma deepens. There is no surviving documentation of these principles. No treatises, diagrams, or textbooks describe their methods. Everything we know must be inferred from the stone itself. And while we can measure microfractures, tolerances, and symmetry, we cannot reconstruct the entire decision-making process. We are left to observe outcomes and hypothesize the knowledge embedded within them. This raises a haunting question. Could technology exist without a written science? Could an entire body of empirical knowledge, equivalent in sophistication to modern machining theory, survive purely as practice and craft, transmitted orally or through apprenticeship, yet vanish with the collapse of a civilization? The stone seems to answer with a subtle insistence. Yes, the engineering is present, visible, measurable, and reproducible, but only if the observer can discern the underlying logic. In essence, the stones speak of engineers without names, traditions without texts, and principles applied without formal theory. They suggest a civilization capable of understanding stress propagation, material removal, and precision assembly at a level that rivals modern pre-industrial machining logic. Yet all of this knowledge was tacit, embedded in practice rather than explicitly codified.
And so, the mystery continues. How did these anonymous engineers develop such expertise? Was it trial and error over generations, empirical observation refined into repeatable methods, or perhaps a lost tradition of teaching and apprenticeship that encoded complex mechanical understanding into the hands and eyes of the practitioner? The evidence in the stone points unmistakably toward intentionality, method, and understanding. If these artisans were capable of managing stress, guiding tools, predicting material response, and executing repeatable processes with consistency across continents and centuries, then our perception of ancient technology must be reconsidered. The tools themselves are secondary. The real marvel lies in the knowledge applied.
And yet, for all the insight gleaned from microfractures, surface polish, and interlocking geometry, the full system remains elusive. We see its outcomes, infer its principles, and attempt to replicate its methods, but we cannot reconstruct the complete thought process of those who created it. The challenge is not only archaeological, it is epistemological. As we step back from the stone, the question crystallizes. What does it mean to engineer without a written science? How is knowledge transmitted, preserved, and lost? And most importantly, what other capabilities might have existed in these ancient cultures that we have yet to discern, hidden in plain sight, encoded in stone, awaiting rediscovery? The stones are silent mentors, whispering lessons in physics, geometry, and material science to anyone who can read their subtle signs. The task is to listen, to measure, and to imagine the systematic understanding that once made the impossible not only possible, but repeatable. The engineers have no names, but their knowledge endures, etched in granite, andesite, and sandstone, a testament to human ingenuity beyond recorded history. Across the vast sweep of human history, civilizations have achieved technological feats that, in retrospect, seem astonishing in their sophistication. Yet time and circumstance often conspire to erase not just the structures they built, but the very knowledge that made them possible. The stonework anomalies we have examined, from the mirror-polished granite vessels of Egypt to the interlocking blocks of Puma Punku, are not merely anomalies of execution, they are anomalies of survival. They demand a confrontation with a deeper mystery. Why did this skill vanish? In considering the disappearance of extraordinary craftsmanship, historical and cultural factors must be accounted for. Take, for example, political collapse. The end of the Mauryan Empire in India, around 185 BCE, coincided with a significant decline in large-scale stone artistry and polishing. Archaeological surveys show a marked reduction in the production of Ashokan-style polished pillars following the empire's disintegration. The centralized resources, skilled labor networks, and patronage necessary to sustain such labor-intensive practices vanished with the state apparatus. The same pattern emerges in the Andes. Sacsayhuaman and Machu Picchu reflect the pinnacle of Inca stonework, yet Spanish conquest and the subsequent collapse of local political structures disrupted traditional apprenticeship systems. Without centralized support, the transfer of complex tacit knowledge was interrupted, leaving precision stonework to fade. Guild and workshop knowledge also plays a crucial role. In many pre-industrial societies, technological expertise was transmitted orally or through practical demonstration. Craftspeople relied on mentorship, repetition, and observation rather than written manuals. In ancient Egypt, the stone artisans responsible for diorite vessels and obelisks appear to have operated within highly specialized workshops, possibly under royal or temple oversight. Flinders Petri, in his meticulous surveys of Giza in the late 19th century, noted that stylistic uniformity among vessels suggests not individual ingenuity alone, but collective codified methods passed from master to apprentice. When these workshops were dismantled, whether through social upheaval, economic decline, or conquest, the intricate knowledge of material behavior, tool guidance, and stress management may have been lost. The specialization of labor without documentation is another key factor. The Inca and Egyptian civilizations relied on intense division of labor. Individual artisans or small teams could achieve unparalleled results because they were devoted entirely to a narrow set of tasks. Puma Punku, with its precisely cut and interlocking andesite blocks, required not only mastery of stone, but also an understanding of block transportation, placement, and orientation. Without written instructions, each generation of artisans depended on uninterrupted apprenticeship. Once political or social structures fractured, continuity was impossible. Unlike written technologies, tacit knowledge embedded in human practice is vulnerable to extinction. Historical parallels abound. Roman concrete, for example, achieved longevity and structural resilience that modern engineers struggled to replicate until the 20th century. The precise recipe, including volcanic ash, lime ratios, and curing techniques, was gradually lost as the Western Roman Empire declined. Modern analysis by researchers such as Marie Jackson and Robert Brune reveals how specific chemical interactions between components produced durability in seawater, a combination painstakingly honed and then forgotten for centuries. Damascus steel provides another instructive example. From roughly the 3rd century to the 17th century, craftsmen in the Middle East forged blades with a combination of hardness, flexibility, and distinctive surface patterning unmatched by contemporaneous European metallurgy. The techniques for producing high-carbon wootz steel, including precise thermal cycling and impurity management, were lost over time, leaving later metallurgists unable to replicate the material fully despite centuries of study. Only in recent decades, using chemical and metallographic analysis, have researchers begun to approximate the original compositions and thermal treatments. Greek fire illustrates a different dimension of lost knowledge. This incendiary weapon, first recorded in the 7th century CE, could continue burning on water and was a decisive military technology for the Byzantine Empire. Yet its composition and method of deployment were closely guarded secrets. Once the Byzantine state's control waned and key artisans died or were captured, the recipe disappeared. Historians now debate its exact constituents, whether petroleum, naphtha, resin or quicklime, because the method of production was transmitted orally, never codified. These parallels demonstrate a recurring pattern. Societies can achieve technological heights, but knowledge that is not systematically documented or that relies on highly specialized apprenticeship is extraordinarily fragile. It can be extinguished through political upheaval, conquest, societal collapse, or the death of key artisans. The result is that monumental structures, advanced tools, and seemingly impossible feats endure while the practical know-how vanishes. In the case of ancient stone engineering, this disappearance is particularly puzzling because the precision achieved in granite, diorite, sandstone, and andesite remains unmatched in some respects, even today. Consider the microconcentricity of Egyptian vessels, which approaches modern industrial lathe tolerances, or the interlocking angles at Puma Punku, which display CNC-like consistency without variation. Or the mirror polish of Ashokan pillars, achieved on quartz-rich stone without diamond abrasives. These are feats that demand knowledge of stress propagation, abrasion physics, material hardness, and process control. Yet none of the associated workshops, tool catalogues, or operational manuals survive. Cultural context offers further clues. In ancient Egypt, knowledge was often concentrated within temple complexes or royal administration. Craft secrets were guarded, sometimes literally by oath or socially by status. Transmission was controlled, selective, and highly localized. A small disruption, political, economic, or military, could sever the chain of instruction. Similarly, in the Andes, the Inca maintained specialized labor systems where artisans were conscripted or assigned to state projects. The Spanish conquest disrupted social organization, led to population decline, and interrupted apprenticeship lines. In both cases, the collapse of governance structures directly affected the survival of technical knowledge. Additionally, technological decline is not always linear. Some knowledge can vanish and later be partially rediscovered, often in a context very different from the original. The Roman mastery of hydraulic engineering was lost in Western Europe for centuries, only to be rediscovered in modified forms during the Renaissance. Damascus steel's metallurgical properties were rediscovered using modern chemistry, but the cultural hands-on understanding of the forging process was irretrievably lost. In stonework, we see a similar pattern. Certain methods may have persisted in fragments, passed down in informal workshops, but the complete system, the integration of material understanding, precision execution, and geometric control, was ultimately lost. The vanishing skill of ancient stone engineers forces a reconsideration of how we define technological continuity. Modern assumptions often equate technological progress with written records or linear accumulation of knowledge. Yet the evidence suggests a parallel mode of knowledge transmission: empirical, practical, and tacit. When a civilization collapses or its social structure changes, such knowledge can disappear abruptly, leaving behind artifacts that are extraordinarily advanced, yet inexplicably unrepeatable. One cannot ignore the psychological and social dimensions of skill loss. Highly specialized laborers may be bound to a particular patron, project, or cultural system. Without that structure, the incentive or framework to maintain rigorous methods disappears. The same artisans who could align granite blocks with millimeter precision or polish quartz-rich sandstone to mirror-like reflection might, under social upheaval, produce ordinary stonework or cease their craft entirely. The disappearance of context, the political, economic, and cultural infrastructure, is as decisive as the disappearance of tools. In reviewing this pattern, a haunting conclusion emerges. Civilizations do not merely lose buildings when they collapse, they lose methods. They lose understanding encoded in practice, transmitted through touch, observation, and repetition. The blocks of Puma Punku, the polished pillars of Ashoka, the granite vessels of Giza, all endure as silent testaments to lost knowledge. Yet the capacity to produce them, with all the repeatability, precision, and sophistication observed, was extinguished. What remains is evidence of mastery, without the manual to replicate it. And yet the echoes of that mastery challenge our assumptions. The sheer scale, the interlocking precision, the mirror-like polish, and the internal symmetry suggest that ancient artisans were not improvising, but applying codified knowledge. Their methods may have been systematic, reproducible, and based on empirical observation, but they were ephemeral in the absence of documentation or enduring social structure. The monuments themselves preserve only the results, not the methodology. As we consider these vanished skills, the question naturally arises: how much of human capability is lost to history, hidden in plain sight within the artifacts we admire but do not fully understand? Could other civilizations have possessed equally sophisticated techniques that were erased by conquest, disaster, or social disruption? The disappearance of stonecraft mastery reminds us that technological achievement is fragile, that knowledge is vulnerable, and that human history preserves outcomes far more reliably than processes. The lessons of lost knowledge are sobering. Roman concrete, Damascus steel, Greek fire, and ancient stonework each illustrate that technological brilliance does not guarantee continuity. Expertise can vanish even as monumental evidence endures. The cultural, political, and social contexts are as critical to the survival of knowledge as the tools or materials themselves. And so, as we stand before the polished granite of Giza, the interlocking andesite of Puma Punku, or the mirror-polished sandstone pillars of India, we confront not only the skill of the ancients, but also the impermanence of human achievement. Civilizations, it seems, leave behind more than ruins. They leave gaps in understanding, silent voids where process once existed. The stones endure, but the skill has vanished, reminding us that mastery is fragile, contingent, and historically ephemeral. And within those gaps lies perhaps the most profound question. If such knowledge can disappear once, could it happen again? The vanishing skill is not merely a historical curiosity. It is a warning, a reflection on the fragility of human understanding, and an invitation to consider how knowledge, even when extraordinary, can be lost if it is not preserved, transmitted, and contextualized. Civilizations do not just lose buildings, they lose methods, insight, and the means to replicate their own genius. The legacy is silent, and yet it speaks more profoundly than any written record. In the quiet observation of ancient stonework, a striking possibility emerges. The artifacts we have long regarded as monuments, symbols, or aesthetic achievements may, in fact, be far more than that. They may be records, archives, and repositories of information, stone as data. This concept reframes our understanding entirely. What if every polished surface, every interlocking joint, every spiral drill hole, every mirror-smooth interior of a granite vessel is not merely the result of craftsmanship, but a deliberate encoding of process, method, and technological understanding? To consider stone as data is to shift from admiration of beauty to investigation of meaning, from contemplation of power to analysis of information. Across Egypt, Peru, India, and Bolivia, these artifacts share a common feature. They carry the signatures of highly controlled, repeatable processes. In Giza, the diorite vessels of the 4th dynasty display internal circularity, with deviations of only 32 microns, far tighter than human perception or casual measurement could appreciate. The interior surfaces, polished to mirror-like smoothness, reveal striations aligned along consistent tool paths, directionally uniform and evenly distributed. SEM studies confirm that these micropatterns are not accidental, nor the result of percussive impact. They are data points, evidence of systematic, repeatable actions. When Dr. Christopher Dunn applied GD and T standards to these vessels, he treated the surfaces not merely as objects, but as outputs of precise workflows, outputs that, like code, could be read to infer method. In the Andes, the interlocking blocks of Puma Punku offer a similar story. The slots, channels, and polygonal edges are not random. They follow standardized dimensions and modular logic. Dr. Jean-Pierre Protzen, in his field studies of Tiwanaku and Puma Punku, emphasized the CNC-like repetition evident in the blocks. Using modern laser scanning, he demonstrated tolerances within a few millimeters across structures spread hundreds of meters apart, carved from highly resistant andesite. Each surface, each edge, each angle is a trace of decision-making, sequence, and constraint management, a frozen workflow preserved in stone. The blocks are not simply architectural, they are datasets encoding geometric and engineering knowledge. The Ashokan pillars of India, composed of single-piece sandstone columns, introduce yet another dimension. Their mirror polish, long admired by archaeologists, is actually an indicator of process fidelity. The absence of visible tool marks implies a high degree of surface control, achieved over large areas and in 3 dimensions. Dr. R. Nagaswamy, in his study of Mauryan polish techniques, noted that contemporary attempts to replicate this finish require industrial abrasives and rotational machinery. The pattern of polish, striations, and uniformity in surface energy is effectively a record of method, the tools, pressure, abrasive selection, and motion applied during fabrication. In essence, the stone carries metadata: how it was made, what processes were employed, and the consistency of execution. This approach is reinforced when considering drilled cavities, such as those in Egyptian granite cores. Flinders Petri's early observations in the 1890s documented spiral drill marks with uniform pitch and depth, which were later confirmed via SEM imaging. The spirals themselves are not decorative, they encode feed rate, rotational alignment, and tool guidance. Each consistent spiral is a data point, revealing constraints and operating principles. By analyzing these features, modern researchers, such as Dr. Dennis Stocks at Cambridge University, have attempted to reconstruct the workflow, the sequence of drilling, abrasive selection, and force application. Even if the precise tools are lost, the data embedded in the stone allows partial reverse engineering of the method. The concept of stone as data extends beyond individual artifacts to entire construction systems. At Sacsayhuaman and Machu Picchu, polygonal granite blocks are tightly fitted, with minimal gaps and stress-managed joints. Microfracture orientations, edge angles, and corner rounding all reveal underlying procedural rules. Dr. Maria Constanza Cerruti observed that across multiple blocks, stress relief patterns align consistently, suggesting that builders applied a repeatable methodology informed by empirical understanding of fracture mechanics. Here, the entire structure becomes a physical database, each stone a record of process, each joint a pointer to methodology, each pattern an archive of tacit knowledge. Even chemical and thermal interventions, if they occurred, can be read as data. Hypotheses such as thermal shock softening, organic acid treatment, or local heating leave microstructural evidence. Thermal gradients may produce subtle changes in grain orientation, microfracture propagation, or hardness distribution. Acid etching may alter surface energy or produce identifiable residues. When analyzed with modern SEM or spectroscopy, these features are not merely byproducts, they are traces of controlled manipulation. In other words, stone can store information about every intervention applied during fabrication, from force and pressure to chemical exposure. The idea of frozen workflows is particularly compelling. Unlike parchment or papyrus, stone cannot be rewritten or corrected easily. Every action, abrasion, drilling, polishing, carving, is permanently embedded. This permanence provides unparalleled insight into the sequence, priorities, and decision-making of the artisan. In the diorite vessels, the internal precision exceeds external finish, implying a conscious prioritization of functional over aesthetic surfaces. At Puma Punku, slot widths, block angles, and corner radii are uniform across entire assemblies, indicating adherence to process standards that span multiple artisans, quarries, and perhaps even decades. Each artifact becomes a dataset, time-stamped, process-encoded and spatially organized. Viewing stone as data also reframes anomalies in a new light. Internal corners, spiral holes, interlocking blocks, and mirror-polished surfaces are not mysteries to be attributed to unknown tools or lost technologies alone. They are data structures. They encode engineering choices, material understanding, and workflow optimization. The variance, or lack thereof, in microfractures, edge straightness, or surface roughness is analogous to error tolerance in modern manufacturing. By analyzing these parameters, we gain insight into both the capabilities of the artisans and the constraints they navigated. Historically, this perspective aligns with broader patterns of recording and transmission of knowledge. In the absence of writing, knowledge could be encoded in practice, in sequence, and in the product itself. Ancient civilizations understood that the object could carry its own instructions. A perfectly polished pillar or a precisely drilled vessel is both artifact and document, simultaneously functional and educational. Apprentices could learn from observation, measurement, and replication, reading the data stored in each stone, refining methods without formalized texts. This aligns with what Flinders Petri and Christopher Dunn have suggested, that tacit knowledge, transmitted through repeated practice and observation, can achieve extraordinary precision without written manuals. Modern engineers, when confronted with such stonework, approach it as a kind of forensic investigation. Just as an aerospace engineer might analyze a component to understand its load path, surface treatment, and failure modes, archaeologists and material scientists read stone for embedded signals of process. The techniques, high-resolution 3D scanning, GD&T measurement, SEM imaging, are essentially tools for decoding data. The artifact itself is the database. Every groove, surface finish, and alignment parameter is a stored value to be interrogated, interpreted, and integrated into a model of production. Even intercontinental comparisons support the stoner's data perspective. The polished Ashokan pillars, granite vessels of Egypt, and polygonal blocks of Peru share a conceptual framework. Surfaces preserve the history of process, joints record geometric logic, and cavities encode sequencing information. Dr. Jean-Pierre Protzin's surveys of Tiwanaku highlight how certain andesite blocks, when analyzed in sequence, reveal standardized modular units, implying that dimensions, tolerances, and assembly protocols were consistent across the site. Similarly, SEM studies of Egyptian vessels and Peruvian granite show that microfracture orientation and surface finish are not random, but repeatable, systematic, and in effect, digitally stored in the stone itself. Even the notion of error becomes informative. In modern data systems, deviations reveal parameters, constraints, and limitations. In ancient stonework, minor deviations in angle, surface polish, or symmetry reveal the tolerances inherent in the process. They provide clues to the maximum achievable precision, the limitations of tools or techniques, and the physical constraints artisans had to respect. In this sense, the artifacts do not merely show skill, they communicate the capabilities, assumptions, and decisions embedded in production workflows. Perhaps most intriguingly, the stone may preserve aspects of lost knowledge that human memory and written records cannot. In ancient Egypt, for instance, high-resolution analysis of diorite and granite vessels has revealed concentricity, circularity, and microstriation patterns that suggest techniques of precision beyond the understanding of conventional archaeology. In the Andes, microfracture orientation and joint geometry encode procedural decisions that vanished with the Spanish conquest. Across India, Mauryan pillars preserve polishing sequences, tool pressure application, and surface energy manipulation that may never have been recorded elsewhere. In each case, the stone itself is the archive. Considering stone as data challenges conventional assumptions about the transmission of knowledge. It implies that the artifacts themselves are repositories of information, capable of instructing future generations if properly interpreted. This reframing shifts the focus from tools to process, from form to function, and from aesthetics to embedded intelligence. Stone is no longer merely passive, it is active, holding a record of the interactions, choices, and expertise that produced it. Yet this perspective also presents a profound challenge. Reading this data requires specialized knowledge, materials science, structural analysis, fracture mechanics, and microscopy. Misinterpretation is easy. For centuries, these artifacts have been admired for their grandeur, but their true information content has remained largely unexamined. Only by combining archaeological context, high-resolution measurement, and engineering insight can we hope to decode the frozen workflows embedded in stone. And so, the tantalizing possibility emerges. If stone remembers, then every artifact is an archive, every surface a record, and every joint a stored algorithm of action. The ancient world, through granite, diorite, and andesite, has left behind not merely monuments, but instruction sets, physical data, and empirical knowledge. Modern science allows us to access these data streams, but the question remains, are we reading them correctly? The stones in their silence challenge us. They suggest that the line between artifact and archive is not fixed, that beauty, functionality, and information can coexist in a single object. They hint at civilizations that encoded knowledge directly into the fabric of their creations, preserving lessons in geometry, process, and material behavior without written word. The stone is not merely evidence of human effort, it is a record of thought, a storage medium of practical understanding, and a message across millennia. And in that realization lies the ultimate question. If stone remembers, then what are we missing? What processes, techniques, and insights are encoded in its surfaces that we have yet to comprehend? Are we looking at the monuments, or are we overlooking the data they were designed to preserve? Every groove, every angle, every polished plane may be a datum, a unit of information waiting to be read, understood, and reintegrated into the continuum of human knowledge. The stone is patient. It does not reveal all at once, but it does not forget. The challenge for modern science, archaeology, and engineering is to listen, measure, and interpret, to read the physical data accurately, decode the frozen workflows, and perhaps finally understand the processes that produce the impossible perfection we see today. If stone remembers, then every artifact is a teacher, every site a library, and every analysis an attempt to read a language written in rock, microfracture, and polish. The question lingers, are we reading it correctly? And if not, what lessons remain hidden, waiting for the right tools, the right methods, and the right minds to uncover them? Across continents and millennia, from the granite vessels of Egypt to the polygonal blocks of Puma Punku, from the mirror-polished pillars of India to the interlocking stones of Bolivia, one truth becomes unmistakably clear. Ancient civilizations possessed a level of understanding that modern observers struggle to fully grasp. These artifacts are not merely monuments of aesthetic or symbolic significance. They are repositories of knowledge, records of process, and evidence of empirical mastery over materials that challenge conventional assumptions about human technological capability. The tools themselves, the copper chisels, dolerite pounders, abrasive slurries, are secondary. What matters is the intelligence embedded in their application, the management of stress, the understanding of brittle fracture, the control of surface abrasion, the precise sequencing of operations. Across widely separated cultures and eras, we see patterns that indicate methodical reasoning, repeatable workflows, and an awareness of material behavior that rivals modern industrial processes. These are the fingerprints of engineers without names, artisans whose knowledge was tacit, transmitted through practice rather than text, and yet whose results endure in ways that defy simple explanation. History also teaches us how fragile knowledge can be. The disappearance of these skills, through political collapse, loss of guild structures, conquest, or the death of specialized practitioners, mirrors the fate of Roman concrete, Damascus steel, and Greek fire. Technological mastery is not guaranteed continuity. It is preserved only through social, cultural, and practical frameworks. The vanishing of stoneworking excellence reminds us that human understanding can be both profound and ephemeral. Yet, even in absence, the stone retains its message. It carries data, frozen workflows, and the encoded results of highly controlled processes. Modern tools, SEM imaging, high-resolution laser scanning, and geometric measurement allow us to read this data, to infer methods, and to glimpse the systematic knowledge that ancient artisans applied. Every groove, every spiral, every polished surface is a datum, an instruction, a clue. Ultimately, what these artifacts reveal is not just what humans could achieve, but how they thought. The ancients did not merely shape stone. They observed, experimented, and refined their methods. They embedded understanding into matter itself, leaving a record that transcends language, culture, and time. Our task is to interpret, measure, and learn, to read the data that has survived when so much else has vanished. The true wonder lies not only in the perfection of the stone, but in the human intelligence it encodes, a silent testament to ingenuity, persistence, and the capacity to master the physical world in ways that continue to inspire awe. The monuments endure, not as relics, but as lessons. If we are willing to see them as records rather than just objects, the story of these ancient engineers, their methods, and their lost knowledge comes alive once more, challenging our assumptions and expanding the horizon of what we believe possible. In the end, the stone speaks. It tells of precision beyond imagination, knowledge beyond records, and human capability that reaches further into the depths of understanding than we have dared to acknowledge. And in listening, measuring, and interpreting, we begin to rediscover not just their methods, but a profound truth about the ingenuity of our species and the enduring mysteries that still lie encoded patiently in the world around us. Thank you for joining us on this extraordinary journey through the universe on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us where we unravel the darkest mysteries of space.